Hello all, welcome back to our channel. In today's structured analysis class, session 2 on continuous beams. In this session 2, we'll solve one problem on continuous beams, how to apply the theorem of three moments equation, also called as Clapeyron's theorem of three moments equation. In session 1, already we know that what is continuous beam and what is the equation of three moments. So this is applied on simply supported end and also the fixed support. So now let us solve one problem on simply supported ends, how to apply this theorem. Now let us see the first problem on continuous beams. Yes. Now let us see the question. So here a continuous beam ABC covers two consecutive spans AB and BC of lengths 4 meters and 6 meters. On the spans carrying external load is uniformly distributed loads of 6 kN per meter and 10 kN per meter respectively. If the ends A and C are simply supported, then find the support moments at A, B and C. Also draw SFD and BMD, shear force diagram and bending moment diagram. So based on the question, first we need to draw the diagram. Here this is continuous beam ABC. So here, support A, only support A, point A, B and C. Here the length of AB is 4 meter, length of BC is 6 meters. On this AB and BC, the load is uniformly distributed load. So here on AB, the load is, here it is given as 6 kN per meter, and on BC 10 kN per meter. This is the load. So now first write down the given data. In given data, write down the how much of load is given and how much of distance is given. So first span AB. On span AB, L1 equals to 4 meters and W1 on AB equals to 6 kN per meter. And on BC, L2 equals to 6 meters, W2 equals to 10 kN per meter. So this is the given data. Now apply the Clapeyron's theorem of three moments to find the support moment at B. Before that, here the support A in the question is mentioned and A and C are simply supported. So already we know that at simply supported endpoints, the support moments at A and C will be 0. Means here, since A and C ends A and C are simply supported. So here support moments MA equals to MC equals to 0. Now to find the TL, then apply. So to find the support moments at B, apply the Clapeyron's equation of three moments. So here hence we get our equation of theorem of three moments already in other in session 1. Again here I am writing that equation for spans AB and BC. So here Clapeyron's theorem of three moments equation, that is MAL1 plus 2MB L1 plus L2 plus MC into L2 equals to 6A1 x1 bar by L1 plus 6A2 x2 bar by L2. So here already we know that the due to simply supported ends, MA will be 0 and L1 is 4, 2MB L1 is 4 meters, L2 is 6 meters, MC is also 0, equals to 6A1 x1 bar by L1 is 4 plus 6A2 x2 bar by L2 is 6. From this equation here, you can write down that 20 MB equals to 3 by 2 A1 x1 bar plus A2 x2 bar. This as equation number 1. In this, A1 x1 bar and A2 x2 bar is nothing but A1 is area of bending moment diagram due to external load on AB. So here A1 is area of bending moment diagram due to external load. So here, due to load on AB, already we know that load on AB is UDL, that has 6 kN per meter. And similarly, A2 is equals to area of bending moment diagram due to UDL on BC. So then, before calculating this A1 and X1 A bar and A2 X2 bar, first we need to calculate bending moment diagram due to vertical loads on spans AB. So bending moment due to vertical loads, due to external loads, means here span AB and BC, or UDL means the bending moment diagram will be parabola. So on AB, the bending moment diagram due to vertical loads on span AB. On span AB, the UDL, so the formula for this free bending moment is W1 L1 square not L2 L1 square by 8. Means W1 is 6, L1 is 4 square by 8. So here it will is 12 kilonewton meter. And similarly on span BC, in this question on span BC also uniformly distributed load is given. So for this, the free bending moment is W2 L2 square by 8. So W2 is 10 is given and L2 is 6 square by 8. You will get 45 kilonewton meter. So these are the bending moment values due to vertical loads. Now let us see A1 x1 bar and A2 x2 bar. Here, now let us see the bending moment diagram on this ABBC spans. So to draw the bending moment diagram, first draw a horizontal line. So we know that due to external load here the bending moment is parabola due to UDL. So here already we calculated just now, and here on AB due to external load, here this shape of this bending moment is parabola, and here this bending moment value is just now we calculated that as 12 kilonewton meter. And on BC, same parabola here, but the shape of the bending moment parabola, but the magnitude will be different because the length and the load will be different. Here this is 45 kilonewton meter. Now we know this bending moment diagram due to external loads, but calculating the fixing moments at the support moments at B. So we know that equation 1, in that the unknown term is A1 x1 bar and A2 x2 bar. So here A1 is nothing but area of bending moment diagram due to UDL on AB. So it is depends upon area of bending moment diagram on UDL. So this is bending moment diagram. This is the shape of parabola. So for parabola, the area is treated of base into attitude. So here the base is AB and attitude. So here substitute this one. 2/3 of AB is 4 meters. Just now calculated altitude, that adds 12, means W1 L1 square by 8. And here you will get this is 32. And x1 bar is nothing but the center of gravity. So for this, the center of gravity is L1 by 2 minus 4 by 2, that is equals to 2 meters. And similarly, calculate A2 on BC. So A2 is also nothing but area of bending moment diagram due to external loads. So here we know this due to external loads on BC. This is the shape of the bending moment diagram. Same parabola due to a radial, sorry, here BC on, we are calculating BC. So 2/3 of BC into altitude. So here 2/3 of BC is nothing but 6 meters is given, and we calculated previously W2 L2 square by 8, then we'll get 45. Here that A2 is totally 180, and x2 bar is also same, L2 by 2, that is equals 6 by 2 equals to 3 meters. So this is substituting equation 1. So in equation 1, already we know that the equation. We'll see the total bending moment diagram. Here we'll draw bending moment, total bending moment diagram. Here this is A, B, C. Along these support moments, just draw a dashed line. Then draw the support moments, and due to vertical loads, draw the total bending moment diagram. Because this is indeterminate structure, so for indeterminate structure we can't analyze directly. We need to apply some theorems on this. So this is the, already know that the given data. Now draw a baseline on AB, a parabola that has 12, and here on BC this is parabola, and here the value is calculated 45, and this is 12. On support A it is 0, support C is also 0. At B will get 31.8. So this is the variation 31.8. Now here this is positive and negative and positive bending moment diagram. This red color above the free bending moment values, that is the positive, and this is in between this, that is negative, below that fixing moment, that is negative, and above the free bending moment again it will be positive bending moment. This is the total bending moment diagram. Okay, let us solve the shear force in next session. Thank you.